50 hectopascal look quite similar, but something may not. It's hard to say. So I guess I'm saying I don't really understand this.
Yeah, I know the geometry can be complex during displacements.
Helps when you hook up the
I
camera.
thought it probably was, but I didn't want to tell you. I guess we can start at 16.
Yeah. Starting. Well, yeah, every winter is interesting out here, and it's about this time of year I start thinking about, I wonder if there are any sudden warmings that happen. I know I heard there was one in January, but so this is my attempt to try to understand what's happening in the stratosphere for this winter. And so to do that, I went to the NOAA website. They have a lot of really nice maps that they maintain. One of them is 850 Kelvin potential vorticity. This current must be one of the really key data points out. And they have daily maps of it. So I downloaded each one starting in November through, I guess I got through March 6th. And, sometimes they have a different variable for a certain date, so there might be a jump. Other times they'll relabel the primary contour so that can jump right as well. But it's pretty fun to look at. And then after making that movie, I had made one for 2014, so I was trying to compare them because both of these springs have been pretty cold. So, and then I started thinking about some of these other things. So it seems to me what we have is a wildly polar vortex that maybe is most closely related to the old idea of a zonal index flow, where if you have a zonal height gradient between 60 north and 40 north, if that's strong, then you have a uniform zonal flow. If it's weak, then you can have a waggly flow. People try to capture this in terms of a Northern Annual Mode Index or an AO index. What I realized last night is that maybe those indices aren't so good for detecting the wildly polar vortex that's relevant for us. And then perhaps maybe we should try to figure out some local index. Anyway, so one question is, the primary question I had in mind is the evolution of the 850 Kelvin PV surface, which is at 30 kilometers or so, useful for understanding mass and temperatures at the surface? That's quite a stretch. That's a long distance vertically away. A lot of intervening layers which behave in a different fashion. It may seem preposterous to think that the two could be intimately linked, but let's try. And then the question that came up in trying to relate this to the NAM index is, does it really adequately represent the state of the polar vortex relative to us when we have a lobe of high PV overhead? Most fundamentally, what is the relationship between 850 kPV and temperature? It's hard to sort out because is there a lot of interdependence between the surface and the stratosphere, or is there not? You could say, well, if you have a cold you have a surface, lower troposphere, then you integrate through that, you're going to have positive relative vorticity, and that would contribute to a PV anomaly a lot. That's sort of a hydrostatic barotropic argument. But then there's all these dynamical nonlinearities, including sudden stratospheric warmings can happen not independently of the troposphere, but strikingly different patterns of what's happening in the troposphere profile. Vortex mergers, that happens independently in the stratosphere. We'll show an example after the major warming in January. The ocean height grew enormously with an anticyclone coming around, just bulged from the Siberian sector and shoved it, the whole polar vortex over and split it, but then it rejoined and it settled over us, which is pretty spectacular to see. So rapid retrogression, that's a common feature. When you have the polar vortex displaced off the pole, it sort of dips into the Atlantic quadrant, and another tilted sheet wraps up by anticyclonic that comes around and it creeps to the Aleutian high, which migrates briefly westward to join and then comes back into position. So this kind of oscillation discovered by Hirota in 78, it's pretty robust with the Aleutian high polar vortex interaction. That's kind of what's happening at the surface. So that would argue against the idea that there's an intimate relationship between 30 kilometers and the surface. But we'll see, it's peculiar. There's a peculiar conformity between the two surfaces. And then we'll compare these two and see how different they are. So I'm just going to show these two things for our temperature variation. And then if we want to, we can look at a few indices of UW-AOS. So just as a very coarse grain view, the 1st of November to the middle of November, to my eye, all these vertical bars are a little bit below average, and so I would call that a cold period. So first half of November. And then again in early December, it was pretty cold. But then it kind of got a little warmer than normal. Near the end of December, I think there was a snow event that was kind of brief, so maybe it was sort of neutral. One of the cold times in the first part of this year, well, it was kind of warm in the first part of January, but then this is pretty spectacularly cold. We're at -27, so that's mid to late January, and then it got warm in early February, and then now it's been pretty cold late February to March. So I don't know if this is a fair characterization. It's cold in late January, early February, and then kind of late. Let's see, and I wrote these down. Let's see how that relates to features in the mood here. Right? So let's go check that. So this is kind of a fake movie. I do this. Oh no, I do that. I have to select all first. And then double click. What is this? Okay, so here we are at 30 kilometers. It's really hard to see the timestamp. It's down here. This is 2018, 11:01. So we're November 1st. If you can see that, I'll try to stop it at certain times so we can better view this. They highlighted this particular contour. This is the polar vortex. It's kind of a triskelion appearance of the moon. This elongated region of small pp is kind of an elongated illusion high. Let's say displacement and normal rotation. Right, so here's, yeah, well, here we go. Early November, there was a lobe of high pp over Hudson Bay, influencing our weather. It seems to coincide in time when it was cold in Madison. Some other features of this would be wave 2. You have a mild Rossby wave breaking where high potential vorticity is being shredded out. This one is the long tail. I guess you'd call this a surf zone. Here's another one happening over here. This is an anticyclone.
Excuse me, Matt. On these images from this, these no images, the black contour was not one you highlighted, it's one that
No, this came just with the image.
What's the significance of that value of PV?
I think that they were saying that this is representative of the edge of the polar vortex in their view.
Okay.
Analysis. Maybe it's a computer that chooses that, but some gradient. I don't know. I'm sort of guessing.
Thanks.
But the units are per PV units, 10 to the -6 kelvins meters squared per kilogram a second.
Does that mean it's probably a proxy for the axis of the polar jet at 850?
Yes. Oh, right. So you can see the tight contour packing here. The PV gradient is large. It's largest where the jet speed maximum is.
That the polar jet or the polar night jet?
Polar night jet.
Polar
Yeah,
night jet.
yeah.
I meant that.
Polar night jet. Yeah, so the speeds that you could expect along the edge of that would be on the order of 100, 110 meters per second. So it's sort of rotating, it just kind of tends to stick over us, but then, let's see, we're getting to November 15. November was cold. All right, now it's starting to shift around a bit. The Aleutian high is growing. See this nice anticyclonic swirl here with a fairly uniform and low PV inside. And that entity is maintained by tropical air that comes around, and when it gets at higher latitude, it'll wrap up anticyclonic. It's conserving place now. This Rossby wave is wanting to break, but it doesn't. The vortex stays coherent, but what is this? This is 1206. Okay. Early December was cold, but mid to late December was warm. So let's see if this thing moves out of here. Well, let's see. This is the 12th of December. Ooh. Looks like the Aleutian high migrated eastward, and it seems to be related to at least there's a temporal correlation with it being warm in Madison. It's a long shredded tail of high PV coming down. Some people call this a transport barrier, or this a transport barrier. But what's really happening is that this error has been brought into juxtaposition with this error, so it's actually in 1 point. So most of December it was over Siberia, and we were basking in pretty warm temperatures. I think even worrying about whether it would snow on Christmas, right?
We hadn't even been to 10 degrees Fahrenheit from mid-January.
I remember you were a little bit like, what's that? It's not probably.
Yeah, correct.
But
It's fine. It was a fine winter.
Yeah, like,
the end of December, this vortex kind of nipped us, didn't it? This took the 26th, the 27th, 28th, 29th, 30th. Well, it didn't get particularly cold, but that does seem to be related to a snow event in late December. I don't know if that's interpretation. And then the polar vortex, oh yeah, this is the spectacular split. So this generally broad distributed Aleutian high just got so massive it extended itself over the pole, which is technically therefore a sudden warming. But not only that, it split the vortex. And then after splitting the vortex, maybe into 3 parts, the 2 main parts separated, and then this is really cool. Blind like that, which is amazing. I've ever seen that before. And then it just settled over us. So this is January 13th. And then after this vortex split up and remerger and westward shift over us, it just kind of sat there, and it was anomalous relative to the whole hemisphere. A very small vortex after that. So
The interesting thing is if you're looking for a polar night jet, it's actually easterly up at the latitude where the polar night jet.
oh yeah, right here. Oh, yeah, that's right. So
Which is
because a minor warming is warmer over the fall. If it's a very deep one like this one, then the winds will reverse in the zone at 61. But this is pretty striking. Okay, so it was cold. This is January 17th, 18, 19, 20, 21, 22. Still there. Now it's trying to get back over the pole. One could argue that even in late January, there's much less solar radiation in the polar cap region. So infrared radiation by ozone and carbon dioxide and a little water vapor, just space, is cooling the highest latitudes more than mid latitudes, and that is a source of positive PV. So it's trying to generate PV. So you can think of the whole winter as a balance between the polar vortex being relatively generated, but being displaced off the pole by the fact that the Pacific is warm and tends to foster an Aleutian high. And this oscillatory displacement leads to a lot of not only radiation.
What date is this right now?
February 1st.
February 1st. So then we had early January was warm, late January to early February was cold. And then see they had a contour jump, and then it goes back. I don't know. This could be viewed as a broad weak vortex, or this is maybe more of a vortex. But 2 gradient zones after that.
So that's now the 600 contour instead of the 480. Yeah.
Yeah. So I guess this is 300 in pink, and that's 600.
So you changed contour intervals?
Well, I didn't select this. All I did was download daily charts and then put them in a folder. So yeah, I don't have any control of it. But I should have the expertise. So let's see, what do we got? February. Oh, here's Valentine's Day. I guess that was cool. The Aleutian high starting to grow again.
Is that a different contouring interval? It's so
Yeah.
big now?
Yeah.
Yeah,
Okay.
it jumps around.
Yeah.
But I'll run it all the way through a couple of times in just a second. I wanted to just see step by step if there's some correlation between, all right, when is this? We have this kind of a eastward extension of the Aleutian high. And this is on February 19th. My little cheat sheet says late January to early February was cold, but mid-February was not, and if it's related to this. And then let's see what happens if the polar vortex comes back. Yeah, so you could say this is the polar vortex, and it's sort of, again, starting to influence Central North America. This is March 1st, 2nd, 3rd, 4th, 5th, and 6th. All right, so
just a couple of points. So it's hard to tell exactly on this where the 480 is, but one of the interesting things, the difference between what we were seeing back in January, we have a cold air outbreak, and what we just saw in the last few days, last week or so, I guess, is the extent, the size of that roughly 480 contour.
Yeah,
It was much smaller
very small.
over
scale.
the upper mid, over the Canada, and now this is a much
you mean
more
in
extensive.
January compared to
Yeah.
present?
And that, John and I have been talking about the sort of the size of the vortex in the troposphere, upper, lower stratosphere, upper troposphere, and how that might control the extent of these colder outbreaks. And so maybe there's some interesting link.
Yeah, because the one in January was so unusual. It didn't get cold further south than St. Louis. Nobody in the South complained about late January's cold in like they did this first week of March. It was really cold.
How about the lack of cold air in Nashville?
Yeah, it's just they're totally different. They were totally different types of cold air
The
outbreaks.
lack of warm air in Nashville. So.
Yeah. Forecasting contest, Nashville one.
Okay, so here we go.
Early January, mid-January, late January.
Do you have a plot of the winds at that?
I haven't done that yet. But from the gradient, you can tell where the winds are,
Yeah.
where the maximum, the wind pedestrian is for the floor area. It would be.
Right.
The only other variable that I looked at so far is 850K temperature. Another one that I'm interested in is actually the very lowest one they store might be 425. And I'm interested in the summertime. Is there any relationship between PV anomalies and weather events? Shell was actually looking at this study on August 20th. And it seemed to be related to kind of a very lazy Rossby breaking pattern involving PV. I don't know, let's see. Interesting. The idea there being that there's such a long range of decay time scale in the lowest stratosphere that the polar vortex is sort of remembered in the very lowest stratosphere a little longer into the summer than in the upper stratosphere, which reverses to the summer. Do those on either.
Matt, I'm wondering, maybe you could take a area average of 850 temperature, 850 millibar temperature.
Like a Midwest average, and a Midwest average for 850 PV.
Yeah, but what I was going to say is,
a correlation.
yes, what I was going to say was you could, once you do that, once you circumscribe the area you're interested in, then you could find what equivalent area at 850K is most often correlated with the time series of 850 millibar temperature. Because it might be that it's a little bit displaced in space and maybe even in time. That could be really interesting to see, what it is that's driving any correlation at all. Just have fun with lag and spatial correlations.
Yeah, it does seem like a good thing. Something like that.
Yeah, because the simple-minded idea, the simplest minded idea would be to just take the 850 temperature at Madison and the 850 Kelvin PV at Madison and see if there is any correlation at all in them. But if you expand it a little bit, you probably see a little bit more clearly what might be going on.
And there may be different types of events, like one is just a small low burst, a broad low burst, and then a trailing wave breaking signal.
Yeah.
Those three seem
Right, you have different varieties probably. Yeah, I agree with you 100%.
So, yeah, 456 is the contour of the picture. Maybe 300 is better. So just maybe one more time do this. So just, it seems preposterous to think that the surface is strongly correlated with something 30 kilometers above the surface, but not so much so in levels in between. How could that possibly? That's a question, and it also invites, distinctly what John just said, that it may not be that there's a direct, exact relationship, but if you allow for some sort of spatial time.
Yeah, that could be really interesting. And then,
this thing is jumping around. Look at this non-linear system in the stratosphere. Right? All that is happening. How is it going to be related to what's happening with the surface? That doesn't seem possible. But
It has been shown, like if you invert the PV at, these really high data levels, that there is an imprint on the surface.
okay,
So,
yeah. So PV inversion theory would say, if you know the PV anomaly at the surface associated with the cold dome, that has a finite vertical Rossby radius of influence, or Rossby of depth, and that it should contribute to. For
yeah.
sure.
I don't know how you get through all the stability in the stratosphere, which is a big barrier, but it has been shown that there is a surface. I can't remember who did it, but.
Maybe a lot of that reason for that is just the hydrostatic thickness argument. If you have colder in the lowest troposphere, then at all heights it's going to contribute to lower heights.
When I've done some analysis, I typically see in these troughs of the polar vortex that they tend to be associated with the polar jets, what we call polar jets in the lower in the troposphere. And in some of the cases I looked at, there's actually a tropical plume coming in between, which splices them downward by reversing the thermal wind and sending the polar jet down. But overall, it seems that when I do a contour analysis of the polar jet in 3 dimensions, with this 5D, I could see it continuing from very high up at 30, 35 kilometers all the way down to the polar jet. Only in the troughs, in the ridges, you don't see that continue, but in the trough parts of this.
In the southern hemisphere, it seems that the polar night jet and the subpolar jet in the upper troposphere are often one and the same, vertically continuous.
Yeah.
In the northern hemisphere, it seems more complex, and I don't know very much about it compared to the southern hemisphere. But it seems like sometimes they are coincident, but other times they're distinct. Is that fair?
I also see that. And the southern hemisphere has more regular progression of these tropical plumes. The pole that connects the two together. Because remember, the tropical plumes are cold to the equatorward direction, so they reverse the thermal wind and pull the wind down from above. And so that's what splices it in to the polar jet below, or even creates the polar jet, possibly. I think this year was interesting in that we didn't have a lot of real strong polar jet activity by itself. It was mostly subtropical jets to the south that worked their way up, but the polar jets were not as much, and I think that was, I'm guessing, I don't know.
Do you think
I'm guessing it's because of the lack of the polar night jet. What's that?
Do you think some subpolar jets are a fragment of the polar night jet, and that some are a remnant of a polar migrating subtropical jet, and some form of the situ form?
Yeah, I think the interaction of the subtropical jet and the polar jet or the subtropical jet and polar night jet can actually create the polar jet. That's what I'm suspecting. This is all
the mystery of the subpolar jet. What is it? Is it a steady-driven jet? Is it a radially caused jet?
It's driven by these plumes of very cold air coming off the tropics and the Jake bubbles that come up. They bring with them very cold air from the tropical direction. It would be elevated isotropic surfaces, kind of gravity wave type thing, very, very long wave gravity wave that moves up the pole and reverses the thermal wind when it gets up there, because now you got cold equatorward direction. And that causes winds to increase upward.
Would you say this process that you're discussing is one way to describe the fact that subtropical jet closes with height, that you have everywhere DTY is positive in the lower stratosphere all day long? In the winter, summer, partly polar plumes of cold air help create that pattern.
Plumes moving forward. Yeah.
That DTY is positive.
but there's a whole
That's right. Oh, yeah, okay, you're right. Yeah, but when you get the tropical plumes, it's a lot more positive. You get these plumes of very cold air coming off the tropics. And I see where those plumes intersect polar night jet. is where you see the jet extending down to the polar jet. It's hard to judge cause and effect just looking at a few pictures, but
It's confounding to my mind that the TDY goes from negative to positive to negative. That imposes some challenge to comprehend it.
right. But I think it's the
We have an
movement of these
opportunity.
tropical plumes that do that.
University of Wisconsin-Madison dynamics group interpretation of what is the subpolar jet in the upper troposphere might be an interesting paper. You know, like this could be.
Yeah. Right.
Colleagues at University of Chicago authored this.
Well, there's a whole class of disturbances in the Arctic that are a function of radiative cooling in the stratus. That's Steve Cavallo's big idea, these polar vortices. And surrounding these vortices, of course, there's jets that probably haven't had any communication at all in the tropics. And yet they show up as polar jet features, I mean, upper tropospheric polar jet features. So I think there's a bunch of different things that go on to create the collection of disturbances in the high latitudes in the wintertime.
It seems complex.
Yeah, it's pretty complicated. But that might also underline why there's a variation in the types of cold air outbreaks. And that's kind of part of what we're talking about here. Some of these are intensely focused on those TPVs, and then other ones are definitely influenced by much larger scale processes. And they can sometimes masquerade as one or the other, even though probably when you dig through the whole data set, you probably realize, no, this looks like, I'm hoping anyway, this looks like a TPV-based cold air outbreak. This one looks more like a much larger scale disturbance. I don't know if there's a way to get that. That would be a really cool thing to have.
So the only other variable I moved it was 850K temperature. And so you can see there's the polar vortex transition from yellow to blue, and yellows and reds are going to be the ocean high or ocean cyclones. This one actually is for February 27th, and it shows that the vortex is fairly much not that different than November 1st, probably kind of getting back to a less vortex. So here's the temperature loop, which is fairly similar, but just visually it kind of highlights different things compared to PV. Because locally the temperature is very similar to PV. It's morphology. You can see the ocean high. This is early December. But then it kind of got warmer as the ocean hemisphere over North America. Then it retrogressed quickly. Look how quickly it retrogresses. So when this dips into the Atlantic subtropics, a little sheet of air comes around, and it'll wrap up because it's getting to higher latitudes. And the combined combination of that plus this causes it to shift eastward over western Siberia. That.
So is that air sinking or something to get that one?
Yeah, I think that's right. So there's a big wave one pattern in vertical motion that is in quadrature. And so just upstream of that, you have substance like 22K per day.
And then over Greenland and Iceland, you have to have almost the same amount of acid. That gets cold really fast.
To approach that to get there.
So that's a hemispheric scale couplet of vertical motion.
Yeah, and the geopotential height difference between those 2 points is 2 kilometers. 1.5.
Oh,
And so it's just this big, huge bend.
Yeah, above the isotropes,
Yeah.
Yeah. That's astounding.
How would you classify that wave? A hemispheric
one?
gravity wave?
Oh, sorry?
No, the forcing, is that a hemispheric gravity wave? What is that?
I think it is. So there were a few papers on this in the early 90s about vortex mergers of anticyclones that come out of the subtropics and go around. And in the Aleutian High paper in 96 with Lynn Harvey, we tried to talk about some of these mechanisms. There seems to be, well, the things that contribute to the Aleutian High, gravity waves don't seem to be relevant until you get to the stratocosm above. This seems to be, sometimes you get an upward extension from the west coast ridge smoothly into the high. But more often what you have is this nonlinear oscillation regime of the primary polar vortex created by radiative cooling being preferentially displaced towards Siberia because there's a cold land mass. But when it digs into the subtropics, air will come around, and when it gets to higher latitude, it'll blow up anticyclonically. And it's just quasi-adiabatic flow. I suppose this does project onto global scale gravity modes or most waves or something. I suppose you could describe it.
Or, I mean, what does the actual flow look like? Is there some sort of crossing of, vortex lines of flow or something in a prescribed, in a systematic direction, so you get positive and negative vorticity vectors? There's no reason why that shouldn't be generating vertical motions anywhere in the atmosphere at high latitude. Because it's such a huge scale, it's amazing. Amazing event.
I don't think that the dynamics of how W and U fit into the temperature and height patterns is adequately. Probably.
But these kind of vertical motions, depending on how deep they are, can be really the source of some of these Arctic outbreaks. When you get the sustained upward motion, it keeps cooling the air.
It really disturbs the stratopause too, so you get unusual stratopause sudden cooling and something. Patterns hard to sort out.
Look at that.
So
Minus 10 at 850 K.
Here's the sudden warming. It looks like it got pretty warm over the pole there.
Yeah.
It's almost, let's see, it's up to minus 20. Oh, that's not that long. We're still below the stratopause. At the stratopause level, at 1,000 K, it's probably no freezing or a little bit warmer. But an interesting thing about the Aleutian high is that in the middle of it, the flow speed is 0, and so all the air in it is communicating radially with what's ever underneath. That's why it tends, I think, to center over the Pacific side, because it's warm. I know nobody's ever tested that with a radial code to see if that's robust. It was first hypothesized by Iron Bowman Slaughter. So yeah, whenever that purple block gets over, so what's this? January 11th, it did start getting warm again.
We got cold.
So this is an interesting point. It does seem that when a sudden warming occurs, and you have a split vortex or something drastic happening in the stratosphere, that then a little while later, the surface flow is more wobbly, a lower index flow. So there's a slight time lag for when cold air appears relative to sudden warming. But much less of a time lag or almost instantaneous relationship between when the high PV blob is ever hit. It's just a qualitative impression.
I'm trying to still wrap my head around what's going on with this setup. Because my first reaction, is there some communication between the two? There's been prior studies that have suggested that there is stratospheric tropospheric interactions. But you sort of think about troposphere to stratosphere, you have to, and further up, you have to have, meet the Charney-Drazen criterion. There's only going to be a certain set of wave numbers that actually make it up into the stratosphere. But I think that's kind of interesting. Our tropopause acts sort of as a filter of those waves as they go up. Once you get into the stratosphere, you only have very large-scale structures, and they can organize in some coherent fashion. Coupled with what Melissa was saying earlier, that then gives you the possibility of getting very large-scale potential vorticity anomalies in the middle and upper stratosphere, because you only have large-scale structures there that they can organize. And so the larger scale that PV anomaly is, the deeper its penetration depth can be down into the.
Oh, so it's selected
Right.
to be deeply penetrated.
So maybe there's this, very high wave number type stuff in the troposphere, as we always see that, but then only a selective number of waves go up there, and depending on how they organize themselves, if you can get a large scale vortex, you can then get something that PV-wise can invert and influence the whole.
For about 20 years, I go to stratosphere meetings, and people are always talking about this downward influence. If you know what's happening at 60 north at 10 hectopascals, then you'll know what's happening in the troposphere for the next 2 months. That stuff. They never explain why. I think you have an actual physical, plausible mechanism. That if you have a large enough horizontal scale, and have a deeper Rossby.
Yeah, right.
Wow. That seems, and then maybe, it could explain how that's coupled to the surface. You have
perhaps,
a big blob over us. I like that. Well, so here's February 14, 15, 20, that polar vortex is still open. But This year is different than 2014, so let's check that out. Maybe first, let's really quickly remember that this pattern for mid to late January after the sudden warming was a small polar vortex right over us, right? So it's and that's really different than what happened in 2014. It was more of a peanut shape. So here, this period of time, just like, well, why are we?
Yeah, that's the coldest day, was the 28th.
And so then we'll try 2014, which only has January through February. So here's January 1st of 2014. And this, the Great Lakes that were more than 95% ice covered.
Yeah.
But this year not so. Lake Michigan is blue. So this is more of a wave number 2 or peanut shaped Logan. And the way I was thinking of this year was there was that blob in the Gulf of Alaska which favored more anticyclonic behavior in the upper troposphere, which maybe sort of kind of qualitatively dents that side of the vortex, the lowest stratosphere. So it becomes a peanut shape. So it's not just anticyclones in the North Atlantic, but also in the North Pacific, and the two of them tend to just kind of get that pizza shape into a peanut shape or something.
It looks like the PV gradient around this thing is stronger too in 2014. That looks like that jet must have been roaring around. Even as the geometry changes, it seems really strong. I don't know if they've changed the contour interval since then to now, but if not, that looks like a stronger gradient.
It looks like the same.
Yeah, so I mean that's resistant to being split or resistant to being, you know, really pushed around.
Yeah.
Maybe compared to this year.
As far as the explanation for why this one stayed large but wobbly instead of
Yeah,
breaking
right.
up and shrinking.
Right. Stronger rotation just makes it harder to put it off its
That's
axis.
Oh, it did break a little bit.
But the repair is fast. The triage is fast. And then it looks more like this year now.
Yeah,
It's
so
weaker.
this looks like now except in Siberia.
Yeah, Robert Blake's.
Late January except in Siberia. Okay, so it was large and peanut shaped, but then a part of the end of it broke, and the response was to recombine into a smaller vortex.
Yeah.
On the side where
For the break.
Almost looks like the area might almost be close to the same. It's just a different orientation.
And then, so I was thinking that I won't belabor this. I have probably in the slides, but it might be interesting to look at maybe a couple of them. I was just thinking, well, to the extent that there's this theory of, you know, the vertical coupling. If you know what the stratosphere is doing, then you have predictability skill for the wobbliness of the polar vortex and the troposphere. The idea, right? That comes from. All right, so here's the NAO index from one version. I looked up several flavors, and this is 2018. And it's positive. That would tend to favor zonally symmetric flows, but your polar vortex was very wobbly, I would say. So that doesn't help me. But understand that here's 3 from Jim Burrell's website at NCARM. This one's the NAM, which might be the most robust. And that last one is 2018. It's pretty close to 0. I can't say that that would tell me. It doesn't shout out loud to me, you could have a wobbly vortex, but we did. This one's sort of neutral, this one's a little bit positive. This just shows that the NAM has a little bit more contribution for the orthogonal function of sea level pressure from the North Pacific compared to the NAO, but essentially it's pretty similar. In a positive phase, you have a deeper vortex, and that amounts to a stronger jet flow into northern Europe. So this is a classic description of that. In high NAM, you have a lot of rain in Scandinavia, and it's warm, so you very light colors, and then in a low index now, Europe is dry and cold. Similarly, over us, we have a slightly stronger influence by the NAM than ENSO in the Great Lakes area, and low index, you tend to have a little more hold times. Here's another NAO index, very weak. This one is another one, very weak positive. So this might be important. So in a high index NAM, round and around, but in a low index NAM, these centers of anticyclonic ridge building tend to amplify. So that's kind of a wobbly vortex. And if this lobe tends to be here, for some reason, then that's a wobbly vortex or low index NAM. I think that this index would then explain it. It does account for things like events of snow in Dallas, much more favored than a negative NAM. Just southward excursions of air down the west coast this year, much more than normal. Just like pattern C in the Golden Delta with snow and Kappa. Bellingham, much more likely to have cold or snow in Seattle during the negative days. So this is kind of the holy grail of stratospheric research. And Baldwin definitely came out with this. But I want to point out what you were saying earlier, the troposphere influences the stratosphere. Mark Baldwin loves to ignore this, but it's true. If you have an event here, it can then influence the stratosphere. This is weak vortex. So if you have a building anticyclone that have a weak vortex in the troposphere, weak index, that will disturb the stratosphere and cause a warming. Well then, if you have a disturbed stratospheric vortex, there's a downward influence that causes a tendency in the troposphere to be more of a wobbly vortex. And then conversely, if you have a strong vortex, which I guess this is a precursor of more zonosymmetric flow in the troposphere, tends to foster a stronger vortex that we're related to at 10 hectopascals. But once a strong polar vortex symmetric forms, you tend to have such in the troposphere. That will tend to bring warm air into the interior of the continents off the Pacific and off the Atlantic. So
Often doesn't have the same lifetime. The lifetime is very symmetric of these influences, aren't they?
yeah,
60 or 80 days. That's a big difference when you get to March 1st.
like in Hoskins at L85, they differentiate between the longevity of anomalies. The positive ones tend to self-destroy in the troposphere because they're unstable and they tend to mix out with self-induced convection, whereas negative ones or ridges can last a long time. They don't seem to self-destruct. Is there something similar going on in the stratosphere? I don't know.
Yeah, I don't know. But, that extra 20 days of influence from an event that begins around time zero is the difference between an early and a late end of the winter, where we're all pulling our hair out on March 8th.
So I guess we were in kind of this regime here, like late January, late February, March, something like that, a little bit. While the polar vortex was pretty disturbed, there seems to be a vertical coupling of sorts. No, it's an interesting problem. This is very kindly provided by CPC and NOAA.gov. And so this is a time height section from the surface. The tropopause is around here. And it shows this precursor of a high geopotential height anomaly in the troposphere, averaged over the polar cap, and then followed by, in this period of time, a sudden warming where warm air went over the pole in a deep layer, causing geopotential heights to rise hydrostatically all across the dome. And then that pattern seems to propagate downward, and then here's a cold period in February, and then another event like February and March. This AO index seems to bear some resemblance in this portion of the figure. February it was negative, but then, it switched to positive, but we're cold in March. So I was a little disappointed. I thought maybe the NAM or the AO index would relate more clearly to what's happening with our weather. This one's hopeless. I can't even understand this now. I think what happens is they're regressing some models on previous analogs that happen in certain NAO indices, perhaps. And so they've done forecasts up to here for 500 millibar heights, and then this is the ensemble for the most recent forecast. Something like that. Should have read the description on the website. But again, there's no signal that really jumps out at me that says what's happening in the troposphere is clearly related to NAO.
So if we're going to go back one slide. Just the averaging that's done there is just 65 to 90. I wonder, is it not capturing our latitudes?
That is a pretty small, yeah, it's just a little, very, very core of the vortex. Yes, I think we need to come up with an index of the total vortex load that is over us sometimes, because when it's a peanut shape and you get one over Siberia, we don't even need to know that. If it's a high NAO and there's a, if it's, sorry, a low index now, and we have like a vortex in the North Atlantic, then that doesn't relate to our whole body. So,
What if you were to take the centroid of the vortex at 850K, and you got to use the same PV contour at all times throughout the whole season. They keep moving it back and forth. You have to pick one that you like. And then you find the centroid, and that's a latitude longitude point, and then the eccentricity of the shape as best you
see,
can.
you're good at these metrics. I kind of have a dim idea of where to go, but that sounds good.
Because that might present you a really nice phase space where you could watch where it is and what it looks like. And then see, maybe you'd have to have a third dimension about what happens in a certain isolated geographic region. But it might be really interesting to try and get some sort of a geometric sense of this problem.
Yeah, this is just sort of a phase of intuition.
Yeah, it's really, really interesting. I think
Leaps
it's
of
a lot.
faith, yeah.
And that almost sounds like something related to the effector, like where you're looking at the geometry and things like that, but it would be centered on wherever your centroid is, not just. I know Hoskins came up with some, average of that where they can pick out it's only elongated in this way or that way because it affects where the energy goes. So.
Yeah, that's kind of what I'm getting at without knowing it, I guess. Yeah.
Right. It's just like I don't think that part of the paper took off, but they kind of write it so we can talk about where the energy's going.
Yeah, there's ways to do this. You can start from simple-minded ideas and really build them to complicated ideas pretty quick, I think.
Your time's let me take up so much time. Would you like to do a quick answer?
I can't stay. I've got to get my lunch in because I got a meeting.
Yeah, I can say just very few words about the weather, probably 5 minutes. I guess the key thing that's coming up, thank you very much, Matt. Yeah, so the key thing in the short-term part of the forecast is our big precipitation event that's expected to start sometime in the afternoon tomorrow. To see if it can work. We'll go to Europe. We'll just go to Digital. So we had a very small shortwave go by this morning, which I think is what triggered some of our light precipitation this morning. That's headed off to the southeast. So you get a little bit of rain and snow in the mid-Atlantic. But the next weather event is taking shape out toward western parts of Colorado. And the forecast is expected to track basically toward the northeast, approaching us overnight tonight, tomorrow morning, but it should be dry through that period. The critical thing is going to be the temperature at the surface. We can just go ahead to 24 hours from now. We'll go to 30 hours forecast. This is just around 18 Z tomorrow. Cyclone's located in northwestern Missouri, and you can see precipitation has yet to start, just about to start in the southwestern part of our state. Our thicknesses are certainly fairly high. We sometimes use the 540 line in the dark of winter to be our rain snow line, but you get to the early spring, you can move that down a little bit further to the south. But if we look at this, the air temperatures, two things we'll look at is basically what is our wet bulb temperature going to be. The air temperatures are basically just around 34 degrees or so. They're around 34, 35 degrees. The dew point temperature is at the same time about 31 or so. So our wet bulb is just above freezing. If you go ahead 3 hours beyond that, you'll see that we actually cool off by just a little bit. And the dew points still stay relatively low. So when the precipitation finally arrives here, we're at about 32, 33, and the dew points are going to be still holding at around 31, 32 degrees. So we're just close to being saturated. And the question is, with a cold ground, a relatively cold ground, cloudy precipitation, is that going to just ice over, or will be just marginally warm enough for anything that falls to stay liquid? I think surfaces that are treated or have lots of salt and crap on them are probably going to be okay, but that's something to watch out for tomorrow. But you can see we have very strong warm advection. You can see this thermal ridge that exists just to our south. It kind of goes back toward the northwest of the cyclone, sort of setting up. I believe if we were to look at this
Because if I do, it's a very nice trowel-like structure associated with this. If we go ahead just another 3 hours beyond this, you can see cyclone lifting to the north, and this precipitation continuing. Probably north of the Dells is probably going to be a region of some fairly moderate to heavy snowfall that's going to be accumulating. Across also into Minneapolis, they're probably going to get a significant amount of snow. But we're going to be just on the line. We're going to be liquid by this time, perhaps. Further to the north, it'll be, there could be some icing, and then there's going to be a region of probably moderate snow all north of Madison tomorrow. We go ahead to 39 hours, so now getting into Sunday morning, or Saturday evening, actually. Cyclone's right on top of us, again, all the snow is long. And if we look back at the temperatures at this point, probably holding a mid 30s, I would imagine this, as well as the dew point temperature, probably for its saturation. So it's going to be kind of a cool, damp weekend, or chilly, damp weekend, with a possibility of a little bit of ice at the beginning of this event, but going over to liquid precipitation. Then by the time we get to Sunday morning, or past midnight on Sunday, cyclone's now well to our east. The beam of us, we're getting northwest winds, with the possibility of chain over back to frozen precipitation as the cold convection commences. But it's really a well-developed short wave, and at the depth of the atmosphere, but you'll see it's the windy and cold, maybe some clouds lingering during the day on Sunday. Temperatures during Sunday, let's take a quick look at what our clock set ahead now will be really bright. Not too bad. Probably mid-20s for this time period. Looking quickly ahead, as I like to do, we'll go back to the surface map. Again, this is a very abbreviated discussion. That's the key thing. I've looked at other models. The NAM is actually a little bit colder, gives us ice, more ice, but if we go ahead into the week, let's go to 96 hours, please. It's Tuesday morning, then ridge over us, and our next weather system taking shape even further to the south. And west of us, you can see lots of warm advection of the Central Plains. Another big warm up, 120 hours, 5 days out. Wednesday, warm advection. I think it's undeniable this is going to be a liquid event at this point with much milder water. So the air temperatures on the at 132 hours. So Thursday at 7 p.m. now. It could possibly be getting close to 50 degrees. So, and for Weather Watch next week, we'll probably look ahead at the forecast then. Go back to the surface, we'll cool off again. Big 89 coming in. Start our spring break with strong cold advection and return to more winter-like conditions. But also we go into the first, just for the 24 hours, it's ended out with good liquid precipitation. So too bad to actually there.
Yeah, it's kind of cold though. 39 or something.
So really, it's part of spring break. And if you really want to just go to the CFS and okay, that's the Tuesday. That's well after we get back. It's nice to look at when we return after spring break. This would be kind of depressing. After a nice, somewhat mild spring break. It's relatively bad this week. It's not going to be so bad. Anyway, again, the key things to watch this weekend are going to be tomorrow. Precipitation starting late in the afternoon. Mid-afternoon. Liquid precipitation, maybe a little bit of ice. Well to our north, it'll be snowy, and then after that, just windy and cold for Sunday.
That'll be a tweet storm, the one off the coast there. It snows in Washington on the 28th of March. We'll hear all about it.
Right. I wonder who would be doing it.
Yeah.
What
are you going to do? What are you going to do?
Something about the locker. But let's go to 540 hours to see how this. Well, this is going to miss us. So it's like, oh yeah, it's still cold.
Snow on the last day of March.
All right.
April 4th.
So John, you have a little smirk on your face. Come on, we're done with it. We're done with it.
Nope. Oh, this is great. But even there, just a little bit of snow on the 9th.
Over Chicago.
Still
We miss it.
last
What we're
year.
doing.
No, I know. Last year's going to be tough. I was just thinking of that, Brad. Next year's going to be tough to beat. That was amazing.
It's 8 for
Oh, the other thing to
Just-
point out, sorry, Pete, we go back to GFS. One other thing, is Sunday. We had severe weather in the southeast this past weekend. That's another 60 hours, I guess. Actually, tomorrow, 36 hours. So as this cyclone begins to rev up and move to the northeast, the possibility of severe weather in the central section of the United States is probably going to increase. If you go to SBC, you can see what their outlook was. They kind of nailed it last weekend. We were kind of hinting at it in our weather watch, but just to see what is. That's the slight risk for today. For tomorrow, day 2. Yeah, it's enhanced risk, so that might be another thing to watch out for. Folks who may need travel over the weekend or just looking at, concern about folks in the central part of the United States and Arkansas and southeastern New York. That's it. Thanks again, Matt, for a wonderful presentation, a lot of interesting questions, and speed for driving. I'll see you guys.
Thank you.
Thanks.